Live.
All right. Hello and welcome to the first FYFD webcast. I am Nicole Sharp, and today I have as my guests Professor Tad Truscott and PhD student Randy Hurd at Utah State University. Tad received his bachelor's degree in mechanical engineering from the University of Utah and his PhD from MIT in 2009. He started the Splash Lab at Brigham Young University in 2010 and moved it to Utah State last year. Randy got his BS also in mechanical engineering in 2012 from Brigham Young University. And between the two of them, they have numerous awards, particularly from the Gallery of Fluid Motion. And their work has been featured on Science Friday, the BBC, Wired, and I don't know if any other fluid dynamicist can say this, but Saturday Night Live.
Yeah! Live from New York.
So we are super excited to have them with us today. And thank you guys for joining us.
Thank you so much.
Hope you guys are excited.
Yeah.
Hope everybody online is as excited as we are. If you are watching on the YouTube channel, you'll notice an annotation in the lower part of the video that says "Be part of the conversation." If you click that, it'll take you to a Google Hangout, and you can submit questions over on the right side of the page. If you see something that says showcase instead of Q&A, go to the little grid icon in the upper left, click on that. You should see Q&A and be able to submit some questions. So if at any time you have questions, feel free to throw those out there. In the meantime, you guys, I think, are sitting in the lab. Was there something that you wanted to start off with?
Sorry, we were just admiring ourselves on the YouTube site. Sorry. Can you ask that again? I'm sorry, we're ready. We really are.
So you guys are in the lab right now, it looks like. Do you have something you want to show us to start
out? Yeah, we brought a bunch of really exciting, we brought a baseball, and we brought a racquetball, and we brought a ping pong ball, and some of these really cool things called wabobas. So the bouncing balls, and yeah, we're really excited. We've even got some water. We've got a tank of water here. We've got some demos we're gonna do. It's gonna be great.
Yeah, so you guys just had a paper that came out in Nature Communications that's actually on the bouncing of these elastic waboba balls. Whoops, there went one. Fortunately, I have two more.
That's good. They're slippery, so.
They are slippery. They bounce pretty well on my desk here, but they bounce a whole lot better on water, which is what you guys studied.
Yeah, exactly.
So tell us a bit about that.
Yeah, sure. So we noticed that these things kind of bounce on the water pretty well during a summer skipping stone exercise, and we can talk more about that in a minute. But anyway, that made us curious. We started taking high-speed videos, which is kind of what we do. About this topic, and what we noticed really quickly was that these seem to behave differently than other types of balls, and so of course we started down this road, and now the paper actually does a pretty good job of explaining what happens when elastic objects hit the water, how they bounce, how they react to that water, and it even goes far enough to say what happens when these things become solid, less elastic. And so anyway, great. It's been a really exciting journey along the way.
Yeah, our readers really enjoyed the post that I did that was sort of explaining what was going on with the bouncing off of water.
We've enjoyed watching all week long, everything from walking on water through, surface tension effects to walking on water by, the cavity that's formed. And then, of course, that relates really well to the stuff we're doing with the skipping balls. So anyway, it's been a lot of fun. It's been a fun week talking about it so much.
Yeah, it's been a fun week for me, too, getting into that topic. So you guys mentioned that your inspiration for the elastic spheres on water was going out and skipping rocks. So what sort of made you decide to go down this route?
Yeah, so I'll just tell you the story really quick. So my son and my nephew and I, and actually some of my other kids were there the first day, but we were out there just skipping rocks. We used to live in Newport, Rhode Island, actually in Portsmouth. And we would go down to the beach there at Sandy Point Beach, and we'd throw rocks on the water surface. And, you know, it's just a lot of fun, and everyone gets all excited about it, and it's interesting. And then we found ourselves at a convenience, like a $5 or $1 store, you know, later that weekend. And we found, you know, these balls, and we were like, these are awesome, you know, or I didn't know if they were awesome at the time. My son and my nephew were like, hey, can we buy these? You think this would be fun to go try out, you know? So then we ended up picking those up and going down to the beach. And of course we were like, these are great, you know, they're so fun. And they're easier for people to be able to throw and bounce, and they go really far. And so of course, my nephew wanted to see what it looked like in high speed. So the next thing we knew, we had taken it to the lab, taken some pictures, showed him, and, you know, I guess the rest is kind of history. That was almost 5 years ago, though. That was in 2010. So anyway, pretty exciting. I guess almost 6 years. Jeez.
And I just wanted to say it was really fun for me because I've been gearing up for grad school for a while, and you kind of get this talk about, you know, grad school is totally worth it, but don't think it's just going to be fun and games. And so when I was talking to Tad Trescott, and he said, yeah, I really just kind of want you to study this toy for your PhD thesis, I was like, wow, this is maybe as good as it gets. And it actually reminded me of a time that my second grade teacher told me you'd never get anywhere in life by just playing with toys. And so this has kind of just been a vendetta to prove to her that that's not true. Like, you were wrong.
Okay, so most of us don't get to go to grad school playing with toys, but some people get to. I think the rest of us get to be jealous of you guys. So you don't just get to like go out to the pond all the time and throw these things in order to study them. You want to show us a little bit about the setup that you've got back there?
Yeah, sure. So what we've got here, Randy, go ahead. Why don't you tell us what we got?
Yeah, so these are some tanks that we had manufactured for, we were trying to do a multi-skip problem. So in addition to the paper that just came out, we're looking at how the physics evolve with each successive skip. And we actually had it set up in a much larger room than this, where we had several tanks like the one I'm showing you here. Notice they have high walls on the side for filling, but they have low walls on the other ends, and that's so that the balls could skip successively from tank to tank. So that's what these tanks were originally made for. This lab, of course, is not large enough to facilitate multiple skips. What we're going to do here is kind of demonstrate single skips, and it just imitates kind of what we did previously when we were doing the paper. We had tanks like this, we had cameras pointing at them, and we would throw and launch the balls inside and have them skip out, take the images, and then we go back. And like you said, not all of the time is skipping spheres. Unfortunately, only about 3 months was skipping the spheres, and then about 1.5 years was writing code to process the images that we had of those spheres skipping. So that's kind of the approach we took to take this data.
Awesome. That's really cool. I have to say, having seen the like drone video of the previous lab where it was set up for the multiple skips, that I'm super jealous of that. That looks so cool.
Yeah, you know, we had so much fun designing that and then going out and using it. And it was we were so lucky to be able to do it in a warehouse. It was really exciting. But one thing we learned really early on is that we shouldn't have put the tanks on wheels, but we should have put them on rails. Because you'd try to move them around, you know, and the wheels would move. And then anyway, half of the time was spent just rearranging the tanks that were full at roughly, 300 gallons of water. So anyway, lesson learned.
That makes for an interesting challenge. All right, so one of the other, sorry?
Go ahead, sorry.
I was gonna say, so one of the other things that you guys are really well known for are your contributions to the gallery of fluid motion. So for those viewers who aren't familiar with this, every year at our big fluid dynamics conference in November, there's a big competition. It's been running for, I think, something like 38 years now. And researchers will submit posters and videos that have to be aesthetically focused as well as scientifically interesting and relevant. And so we actually have a big competition every year to see who wins awards for this gallery of fluid motion. And Tad's lab is kind of infamous because over the last 5 years, how many awards have you guys won? Usually they win like multiple awards a year. Lots of people are jealous of you guys.
We've only won multiple awards once, so I should say that. And over the last 10 years, we've won 8 times. So it's good. We've done really well, and we're super happy about it. But we're just mostly super interested in. We love aesthetics in our lab, especially me. I just really love taking photographs. So I mean, we're super happy when we win, of course. We get really thrilled about it, and we take everyone out to dinner. It seems like we are also just we just really love what we do. So I don't think the winning is necessarily that. It's great, and I'm so glad they have the contest. But we're also super glad to just participate. And like you mentioned, there are probably 100 poster entries and maybe getting close to 100 video entries every year. And so there's just so many exciting things to see. And it's so fun to see how different researchers look at the same problem. Because a lot of times these are similar problems come up from year to year. I don't know, I love it. It's great.
It's true. So the number of posters and videos fluctuates from year to year, but it's definitely turned into a thing where everybody goes to the conference, and you have to set aside some amount of time to go check out all of the posters. And we put up this wall of 8 televisions that are constantly playing video, and there's a lot of great stuff. So what I was interested in was actually hearing about from you guys what some of your inspiration. So the topics that you guys have covered in those Gallery of Fluid Motion videos and posters over the past few years have included all kinds of things, including the balls bouncing on water, but also having sort of smoke-filled bubbles that get burst, or most infamously, I believe, are the urinal dynamics, which is what got a lot of attention in the past couple of years. So where do you guys get your inspiration for this stuff?
I don't know.
Well, I think that's one fun thing about our lab is I think for many people, inspiration maybe comes from other literature, which of course is a good way to do it because then you find the gaps in literature, or it comes from maybe more technical obstacles that people are trying to overcome. I think often, not that we're not inspired by those things as well, but I think often we're kind of just inspired by everyday life. Whether we're just cooking a curry, or we're doing something outside, and we're wondering, something as simple as going to the beach. We're like, why is that happening? And I guess, fortunately or unfortunately, depending on how you look at it, sometimes you're there taking a pee and you're asking yourself questions as well. And of course, I think those kind of questions are interesting because I think they're just things that everyone can relate to. I think every scientist is interested in them as well. But the fun thing about those fundamental questions is even someone without a background I guess the scientists may be interested in how Reynolds number is involved with tripping turbulence, but I don't think the average person is terribly interested in that. But I think everyone wants to keep their pants dry. So
I think I'd step in too and just say one of the things we really try hard to do is tell a story, and we try to do it with as few words as possible. You've noticed this in these posters. They do have some words on there, but you're really trying to tell the story with just the photographs. And it's really harder than you think, to do that. And I think that challenge, for some reason, really, really intrigues us, or at least me. And so not only are we curious and excited about these problems, but then it's really interesting to me how you might tell that same story with a series of images or with a video, or how do you unravel that? How do you let the public know what you're researching is interesting and has relevance maybe? And I think one mistake too that we, a lot of times people will ask us how is this going to benefit society? And I do appreciate those questions. I think we do have to ask ourselves how we're going to do that. But I also think I think one of the things we're trying to show too is that it's not so bad to just be curious and try to find things out. Without that kind of curiosity, we may not be where we are today. You have to kind of go outside the box and not worry as much maybe about an application sometimes, and think a little bit more about why is the sky blue? It doesn't really, just because the sky is blue doesn't change how we engineer much. You know what I mean? But you still want to know,
No, that's a great point. And I know that I've heard a lot of people suggest that one of the things that makes scientists become scientists, or people become scientists, is because they sort of keep the curiosity that they had as kids and don't really lose that. We're always questioning what's going on and why is the world the way that it is. And I think that's part of what makes us tend to gravitate towards science. I really appreciate also what you had to say there about visuals and trying to tell a story that anyone can appreciate without a whole bunch of jargon, because of course that's one of the things I try to do with FYFD all the time.
Exactly, you do a very great job of it. It's awesome.
Oh, thank you.
I don't know if you know, but we also brought some balls we thought we could throw into the water. Do you want to see a little demo?
Absolutely, let's do it.
Okay, so Randy, you
do them on land first.
Yeah, yep. Okay, so I'm gonna hold the camera here and kind of try and help out with the. Okay, let's see. Is there any way you can turn the camera? Like if I do that, can you turn the camera?
I don't think I can.
Okay, that's fine. I want to make sure that I want to make it easy for our viewers to see. Okay.
All right, so here are 4 balls. We have a ping pong ball, a boba, a racquetball, and a baseball. We're going to see what bounces the best on land. Here we go. All right, so it looks like racquetball and ping pong ball are definite winners. They both do pretty good. I think the racquetball is the winner, and then the baseball is awful at bouncing, go figure, and the Woboba, not much better. They're both kind of bad bouncers. So let's move to the tank.
And Nicole, as you know, that's sort of coefficient of restitution. I think you've done several pieces on that before, so we can talk about that in a second. But now let's see what happens when we, apply it to the water. I can't see very well. Let me make sure I can give you a good. How's that look, Nicole?
That looks pretty good from here. I can see most of the tank.
Okay, so we'll get the tank, but we won't get Randy. Okay, there we go.
All right.
Baseball to skip on water. Nope.
Oh, no. Nope. No for the baseball.
Oh, that didn't happen.
Okay, racquetball didn't work either.
Ping pong ball.
Nope.
That didn't happen. This is our last hope. Everybody, cross your fingers.
Oh, yeah.
Where is it?
It bounced back in.
It bounced back in?
Skip.
Did you see it bounce back in?
I saw it bounce back in, but I also saw it skip.
Okay,
Wait,
good.
One more time.
Okay, one more. Here we go. Wait, let me get a good angle. It's really hard for me to see the screen. Okay, is that good, Nicole? Is that?
That's pretty good.
Okay.
Okay, I'm gonna try to get it back in again. Yes, I got it back in.
It's bouncing it off this other glass tank.
Wow, that is impressive.
That's awesome. Yeah, so there you go. It's pretty cool.
I gotta say, I think you guys are a bit better than I am at skipping Wobobas. I tend not to do very well when I take these out.
Yeah, so I think, just as a quick note to the viewers, and, anyone that's read the paper, maybe seen some videos might have already picked this up, but, the Woboba is elastic, and so it can flatten out, which is part of the reason why it's able to bounce so well, because it has more lift force as you increase area. And, lift is based on area, so that's easy. And then the racquetball also is flexible, it's elastic, but not as easily deformed. And then also the racquetball responds to its elasticity more quickly, right? It returns to its original shape faster. And the Woboba has a slower response time. And if you watch any of the videos, you'll see there's this, for some of them, the Woboba hits and it flattens out, and there's a wave that is traveling backwards on the Woboba. And if that interacts with the cavity before it leaves, it tends to fail.
Mm-hmm.
So those are the ones where you see kind of 2 bumps.
Yep.
In the water. If you do the same with a racquetball, and I think the supplemental video shows this, but if you hit the water with a racquetball at, say, the same speeds we were using, it responds very quickly. So it has maybe this responds at 1,000 hertz and this responds at 10 hertz, And so you can see this racquetball going into a mode like this, And what's cool is you can see the water kind of flicking off of it on each of its expansion and contractions. So it's kind of cool. So racquetball can bounce on the water, but it's limited in what angles, and there are more limited angles and more limited speeds where it will work. Whereas the Woboba has a broader range, which makes it easier to skip for so many different people. Even my 6-year-old daughter can skip a Woboba, right? But she can't skip a racquetball, So that's kind of cool.
Yeah.
She can't skip a stone very well either, to be honest. Anyway.
Excellent. That was a great demo, guys.
Okay,
so I just want to add in again for the viewers, if you're watching on YouTube, there's a link across the bottom that says you can be part of the conversation. If you click that, it'll take you to a Google Hangout window. And over on the right side, you should get a chat window if you have any questions. If you don't see the chat window and you see something called Showcase instead, look in the upper right corner and there's a little grid icon. Click on that. You should be able to choose Q&A and be able to submit questions. So if you have any questions, please let us know.
So let me ask you, do you have any idea how many people are watching? We've got an audience of 2 or 3 or?
No, we're all the way up to 6 right now.
Yes. Okay, great.
We're 6 on the live, but we're also recording this because there are a number of people who couldn't tune in. So people will be able to see it afterwards as well.
That's great. That's great.
I didn't realize that you guys can't see the viewer count, but I can.
No, it's fine. It would just make us nervous, you know. That's all great.
No worries. No worries. All right. So let's talk a little bit about your background. So what brought you guys to fluid dynamics? What made you interested in the subject? It's not a subject that most of us have early on in school. So I think it's kind of interesting sometimes to hear how people found their way to it.
Yeah, I agree. I'll try and make mine short, and I think Randy's is different. So we both have.
Yeah. You should both answer.
Okay, good. So when I was a kid, my father, when we were about 10 years old, he bought a sailboat for our family. It was a catamaran, kind of like, you know, a Hobie cat. It has 2 holes and a sail. And we would go out on this thing. I remember our very first time we went out, my father took us to this lake called Deer Creek, and it got really windy, and he had no idea what he was doing, to be quite honest. We had to have someone in the parking lot help us put it together that also had a similar boat because we didn't know anything about it. Anyway, we got out on the lake and it got really windy, and my brother and I were on it with him, and we couldn't control it, and so it tipped over, what they call turtle, where the sail is now underwater, so the whole boat is inverted, and of course my brother and I we weren't trapped underneath, but that's the story we like to tell. Like, we were trapped underneath this thing, and so of course we survived, but it was a terrible experience. And I'm not sure if my brother fell in love with it or not, but for some reason I've always been a thrill seeker and just a super curious person, and so I could care less that I was hurt or almost died. I was ready to do it again, although I was freezing. And so that led to me just really loving sailboats and falling in love with the sport. And so when I went to grad school, one of the things I was looking for was naval architecture. I really wanted to design boats. And in fact, some of my essays to get into grad school talk about this idea of improving sailboats to the point where they can maybe hydrofoil and hydroplane and come out of the water. And so, I never really got to fully realize that dream. I took some courses on it, but I wasn't able to work under someone who did that. But what was cool was a couple summers ago when they had the America's Cup.
Yeah.
And, the America's Cup with those boats with the hydroplaning and everything. Oh my goodness. I was just like, I was like a kid in a candy shop. And of course, I'm just so thrilled to see something like that actually happening on a worldwide scale. So that's a lot of fun. So that's my story. That's how fluid dynamics became my thing. And when I went to grad school, I was really lucky. My advisor bought one of the first digital high-speed cameras out there. And so of course that was the first thing we started doing was high-speed digital camera imagery. And then I got into photography and all this. And I don't look back on it with any regrets. I mean, it's just, and I still sail. So I was going
to say, you were probably in the MIT sailing club, weren't you?
Yeah, absolutely.
Yeah, I've gone out on some of those MIT boats a few times.
Good times. I've had a lot of good times out there.
Yeah, sailing the Charles is fun.
It's not fun to fall into. That place is nasty, but
Yeah, I let somebody else be in charge of driving, so I don't go falling in.
There you go.
That's a key. All right, Randy, how about you?
Yeah, my story is a little different. I remember being kind of young, I don't know, maybe a young adolescent struggling to find meaning in life. And I believe it was MIT that did some of this first high-speed imagery where they were looking at bullets. Mm-hmm. And they were looking at, I remember this video of the bullet tearing through a card. So they had a playing card with a queen of hearts.
Doc Edgerton.
And then, this bullet tears through that card. And I just thought that was fascinating to see things happening that slowly. There was this whole world that you couldn't see because you were incapable of, I guess, perceiving things that happened that quickly.
And I was fascinated by that. And I'd always kept that in mind. And then I had this really kind of eccentric, strange, high energy teacher at Brigham Young University that taught my instrumentation course. And this guy just happened to be studying high-speed photography. And so it kind of like re-excited that idea in my mind. And I thought, oh, I'd really love to get involved with that and kind of see how that works. So I started working with this guy, and we worked together a little bit when I was an undergraduate, and then I got brought on with graduate school at Brigham Young University with Tad, and then I actually got my master's degree at BYU as well. And then, yeah, you know, now we're here together. So it's kind of funny. I was more intrigued by the imagery and actually a lot of this type of stuff you show on FYFD. And so, yeah, that kind of stuff really made me want to, I guess, ask more questions and strive to be more involved in the scientific community. I didn't know about the Doc Edgerton part. Really?
Yeah.
I love it.
That is cool. All right, so speaking of questions, we actually have a listener question. So they would like to know what other toys you have there in the lab because they think it looks like a mixture between a car workshop and a kindergarten. Just kidding.
That's a really accurate description, yeah. I love this. All right. Well, here's one we've got right here. So right here, we've got a toy right here. Thank you, Alvaro. I hope I'm saying your name right. Thanks so much. This is great. So Randy, tell us what this is. Right here, we've got this toy. Oh, well, we have a lot of syringes. Yeah. We have a syringe in every corner. Okay.
Toy is maybe a dangerous word to use for this, but this is when we were doing our urinal experiments. We wanted to be anatomically correct, and so because at first I was using something like this, like a syringe, to simulate the urine stream, and that wasn't quite accurate because there's kind of an elliptical nature to the male urethra. So we printed this thing, but you kind of feel awful holding this thing in your hands. Like you don't really want like someone you don't know to walk in while you're doing any sort of experiment with this device. And we also weren't sure. We kept calling it a urethra, which sounds awful. Like, can you pass me the urethra? So we decided a more scientific name would be the Water Angle Navigation Guide, which doesn't stand for anything in particular. It's just, you know, a representation of what this is. So Water Angle Navigation Guide right here. That's pretty interesting.
We've got all kinds of stuff. So in the corner there, let me see. You can see we've got a ladder and a big tank. This holds about 600 gallons. Then we've got, let's see. I've got my bicycle here. Can you see it through the tank? I don't know if you can see.
Oh yeah, I'm gonna need a closer look at that.
Oh, okay. So we've got a Scott Spark. This is my first mountain bike.
Oh, nice.
We've already got a lot of curious questions about this, so maybe for another show. Yeah. And then in the corner here, this is our urinal study stuff, and you can see we've got what is that? A tank. Well, we fill that with water. We set it at a certain height, gives us hydrostatic pressure. Obviously, we've got a bunch of
ladder is what you're saying.
Yeah. Yep. A lot of oscilloscopes and. Look, this is even like a light here. We've got can you see? We got a light here. Yep, and then we've got a laser. This is a laser. So we've got like this big laser in this container here. It's not on right now, obviously. We put it in there when we're not using it, and this is its chiller. It has to be cooled. Nd:YAG laser, 200 millijoules, pretty great. It is kind of like a car workshop. Look, we've got a generator in here so we can go outside with the power. And then I think he'll enjoy this. One of my students wanted a rope in the lab so that he could do, you know, pull-ups or whatever. So he just climbs this rope sometimes. Isn't that funny? Yeah, and then look, another tank here. This one is doing a really interesting experiment with soap film. So we put in soap bubbles here, and they grow to 1 or 2 inches in height. And then we drop spheres into that, and it oppresses splash, which is really quite exciting.
And we also have bathtub blocks.
Bathtub blocks.
Oh, those were some of my first fluid dynamical toys.
Yeah, and they're so useful. You can put like syringes in it and then stick it to the wall and then take your data while it's, you know, squeezing out or whatever. It's really great. Yeah. Nice. Anyway, then we just have a shop here where we can make stuff. And then now we're back to where we were before. Oh, no, one more. This one's super fun. I don't know if I can turn this one on, but this one right here, you can see there's a tube here with water, a little nozzle coming out the bottom. And so we're making droplets, but we can make droplets from, you know, basically 40 hertz to 5,000 hertz. and they make a cavity here, and it's really, really cool. But we don't want to give away too much about that. We're not published on that yet, so still working on it.
All right, fair enough.
I hope that answers the question well. I don't know. It's kind of maybe too much info, but it's nice.
No, I think that was awesome. That was perfect.
Okay, good. Get a sense of the lab's like, oh, and then we have a refrigerator and an eating station, so you can stay late and work hard.
Well, see, that's an advertisement you're not supposed to make. I mean, it's probably also not good for the whole recruiting students thing that you're like, yeah, here we are in the lab on a Saturday.
Oh, yeah, that's true. I didn't even think about that. But
this normally doesn't happen ever.
Right.
There we go. There we go.
Saturdays.
But we do like what we do. I mean,
Yeah, we love.
I don't know. You can't complain too much, although work-life balance is important.
Speaking of work-life balance, let's talk a little bit about what you guys do outside. So, Randy, I know that you spent some time doing a lot of STEM outreach with underwater robots.
Oh,
Would you like to tell everyone a little bit about that?
yeah. I wish I had a prop here, but we don't have anything assembled. Yeah, that's actually, if you're in Utah on March 24th, come to the Lehigh Legacy Center, and you're going to see about 850 middle school students showing off the robots they've built. It's funny. Dr. Truscott got a grant from the Office of Naval Research to really just enrich their program for outreach. So they just wanted to be a little more scientific, and so we decided to make some simple instruments that the students could attach to their robots. But as we were doing that work, we felt like we didn't have a real understanding of what this program was all about. So we thought, well, let's just start a little one and kind of see how kids react to it. So I think initially we thought, 20 kids, we'll teach them how to build robots. It'll be fun. We'll learn a lot.
One class.
And then, 3 years later, now we have 800 kids and like 15 teachers and like half of the valley's doing it. And I think, one, we just have a problem. We don't know when to stop. But two, it was really satisfying. I think, it's very satisfying going to a conference and presenting your work. But I think I even felt more satisfaction. You teach these kids, and it's so hard, and like even basic ideas like simple circuits and buoyancy, they're struggling with it, and they're like, I'm never going to understand this. And then you come that last day, and you see them with their robots, and they're driving around in a pool doing a task, retrieving rings, things like this, and they're just so satisfied with themselves. And a lot of them just really want to be engineers and scientists after that. So
yeah,
I don't know.
We even have a kid from 4 years ago when we started it, who visited our lab a couple weeks ago, and he's going to join the lab when he comes to USU as an undergrad. So that's kind of cool, to see it all wrap around again.
Yeah,
so
that is really cool to see come together like that. It's awesome that you guys are doing that sort of thing.
Let me just say, Sea Perch, for those who don't know, it's a program where you build an underwater robot out of like PVC pipe and really basic materials. And when we say robot, it's actually remotely controlled. So you make a little control box, and a wire is connected to it that goes down into the water. It's really a lot of fun. There's a little obstacle course they go through. But it's a great project, especially for people who aren't sure they even know what robotics is. It's a great start. So it's really meant for sort of middle school age kids.
Yeah, I think if anyone's interested in that, maybe for their kids or anyone they know, seaperch.org is a great website, and then utahrov.com is also a really great website they can go to.
Mm-hmm.
All right, so we actually have another question. Joe says, aesthetics have come up a few times related to photography, high-speed video, or the gallery of fluid motion. I'm wondering if you've done things in the lab just for art, and is the university supportive?
That's a great question. I would say the university is very supportive of this. We're still in the process of trying to get more involved with the art community, which is just a building away, which is nice because we're close to them. So we're working a little bit with a guy named Mark Coven and a few others. But anyway, and we're trying to actually come up with some ideas for installments so we can have our art on, on display and see what the response is to it, right? We're just kind of that way. We're also really interested in fountains and fluid interaction type stuff. So I could see more of a permanent thing happening eventually, if that makes sense. And then your other question, so that would be the support level. They don't really pay us to do the art, And I guess, if you were a faculty member or you understand a little bit about how universities work, Joseph, there are, you get this like piece of paper that says how much time you'll spend on different things. And mine's 55% research, 40% teaching, and 5% service. So, art doesn't really fall in there, although I can use creative works in my research to some extent. So, but as far as support goes, the College of Engineering here is really supportive. They love it when we win a gallery or when we participate. They like to put up our posters, and they put them on their website. So if you go to College of Engineering USU, you'll see some of our photographs, at least, are up there. And then your other question is if we do things just for art's sake. And the answer is, to some extent, that is true. So last year, I spent a bunch of time in Belgium and really started to read more and get more involved with art history and things like this, and met some really key people over there that do all kinds of science around art. So one of the things they do is, they use like particle physics, particle accelerators to send particles through the painting to maybe see the different layers. And so, for instance, this summer I learned that a lot of artists will paint over a painting. So they have more than one level to that. So that started to fascinate me. And then working with Baptiste Texier and Stéphane Delolo and Nicolas van der Waal and Florian, we were able to sort of look at paint itself. We started asking lots of questions. So if you have a bunch of paint on a surface, I wish I had some of these here. You can just, you rip off, if you put two pieces of paper together with paint in the middle and you rip it off, you can create this technique called decalcomania. It actually turns out the thickness of the film, the type of fluid, and the speed at which you pull it will actually determine how many ridge lines are formed. And Max,
I got you covered, Tad.
Okay, great. Max Ernst, yeah, this is great. This is something we made and handed out at DFD this year, Division of Fluid Dynamics.
Yeah,
you can see those ridges in there, and this is 3 different colors put together. Xiao Pan, my grad student, made this one, or one of our undergrads. And we're just, we've handed these out at the conference, so it's really fun. That's decalcomania, and like I said, Max Ernst is a good place to start. You can kind of see how he takes that idea and makes not only trees out of it, but even humans, and anyway, really exciting. So then the other question is, what we did was droplets. Do you have one of those there too, Nicole?
Yeah, I do. Believe it or not, I have props.
This is so good. So you can see that when 2 droplets impinge on one another, you get these really cool filaments forming. I don't know if you can see, there's that red one in the bottom corner.
A little bit hard to see, but there's one down here that's like the twisted red and white one.
You have a white background for that, Nicole?
I don't know, but it looks great. Anyway, the twisted background, yeah, so it's hard.
I can't see what it's hard to make the
maybe we can
camera focus that close.
But essentially what happens is the 2 colors mix and merge as the crown, or the corona that's formed, starts to break up. When the corona breaks up, there's a force there, and these things twirl up, they twist, and then when they land, they either make a filament that looks kind of like a candy cane, or they land in a droplet that looks like a big swirl in the droplet. And so the physics behind that, actually, we can unravel, which is really exciting. And I guess to come back to your point, Joseph, is just that the answer is yes, we do creative stuff like this. We get really curious, but it almost always ends up going back to physics and asking the question, like, what is going on? So to do it just for art's sake is maybe not quite right, because we don't just leave it there. We usually go a little further, which perhaps in some people's minds ruins it. And I'm sorry to say that. Anyway, sorry, there we go.
No, that's awesome. Actually, I'm really glad that you got a chance to talk a little bit about that art work that you guys have been doing, because a number of people recently, I think, are getting into sort of the fluid dynamics of modern art techniques, which is pretty cool to see.
I think so too. And I wanted to mention one other thing, and that is, it's really fascinating to me, and this is something it's very hard to study. Watching an artist, it's like they understand the physics so well. I'm trying to unravel it mathematically or model it somehow, or and then image it. And these artists, they just go in there and they just do these cool things with their hands, and then before you know it, it's a face, or it's a whatever they wanted it to be, and you're just like, what? And they don't know anything about the math. They just know how to do it. They just have a feel for it. I think that is cool. Yeah,
they have the empirical understanding of physics.
Yeah. complete manipulation of it is in there. You know, they understand it. It's awesome. Cool.
Awesome. Well, so I've been asking a whole lot of questions. I don't know if you guys had any questions that you wanted to ask to go the other direction.
Yeah, I think we had a couple actually.
Yeah, I have two for you to maybe start off with. First, I was curious what kind of got you down the path of FYFD. I mean, what inspired you to, you know, to do all this?
All right, so I assume you mean what inspired me to start the website as opposed to what inspired me to name the website.
That's coming later. We have another question we want to ask about.
That's coming later. Okay. Well, so I started FYFD as a graduate student. I was in Texas. I'd been there for about a year. So I had my master's degree already. I got that at Cornell. I'd gone down to Texas A&M and started doing a PhD there. And I was also an experimentalist. And unfortunately, the facility that I needed was not available. And so I had quite a lot of downtime early on in my PhD where I was just sort of doing other things while waiting for the chance to be able to do my experiments. And I sort of looked around and I was frustrated by the fact that fluid dynamics was something that really shows up in a lot of people's lives. It has daily importance to what we do, but is not something that gets covered really in a lot of the traditional news media and the traditional science news media. And I felt like, why did I have to wait until my junior year of engineering to learn about this cool thing? So I decided that I wanted to start just every day going out there and putting out something that was cool about fluid dynamics that was written in such a way that anyone in a general audience could understand it. Like you didn't have to have 5 semesters of calculus and 3 semesters of physics in order to appreciate the subject. So that is how FYFD came about.
That's awesome.
Yeah, good answer.
That is so good. Okay,
Question number 2. What does your grandma think about the name of your website?
So to be fair, my grandmother died before the website existed.
that's not fair.
That's not.
Yeah. So that I think she would probably be supportive of the website and interested in it. That I think probably very much like my parents, she would at least initially look askance at the name. But I think they've come to appreciate it for what FYFD does. And they sort of appreciate that the name is not the most important part of it, what I'm doing.
Great.
So let me ask this then. I mean, you must have reasons. Why the name then?
Why the name?
Because obviously it matters, right? I mean, we pick names, right?
It's true.
So, you know, it is, I agree, I like the name, but it does take time to grow on you, you know, I think so why, you know?
Well, so the name doesn't take time for certain people, for it to grow on certain people. Some people seem to like it right away, and I think that actually has helped with the popularity of the website.
Yes.
But the actual reason behind the name was that there was a meme on Tumblr in 2010 when I was looking at starting the website, and there were all these blogs that were F yeah this and F yeah that. You could find them for whatever TV show or like sports team or fandom you could imagine had one of these. And I think there was a chemistry one and there was a math one, and I said to myself, well, why not F yeah fluid dynamics?
That's awesome.
So, I decided to do that without ever imagining that the website was going to become as popular as it has, or that anyone was ever really going to know that I did this. I don't know if you know this, but I spent the first 2 years or so doing FYFD anonymously.
Oh, yeah. In fact, was your coming out when you went to that conference kind of thing? Didn't you come to APS and talk about it? And wasn't that kind of like when you just opened up about? Is that right?
Yeah. So actually, in 2012 was the first time at APS that I admitted to somebody who I didn't already know that I was the one who was doing FYFD. And the response was overwhelmingly positive. And that kind of convinced me that I should come back the next year and actually own up to it and give a talk. So 2013 was when I gave the first FYFD talk, which was after happily people were able to help me with my crowdfunding so that I could afford to go to the conference and it's about FYFD. But that was actually that was where we met.
I was gonna say, I think we met right after that talk, actually. But I mean, at the conference was definitely when we met, 2013.
Yeah.
I'm loving this comment by Alvaro over here. He's like,
yeah.
This is actually my answer to that question. I would have never followed a blog called "The Beauty of Fluid Dynamics."
There you go. So calling it what I called it actually helps make it more popular. I think it definitely helps, especially with younger crowds, because fluid dynamics, weirdly enough, is kind of a dry academic subject, despite the topic. And so I think having that sort of silly name helps a little bit. I
do too. I love it. It's great. It's a great website too. It's so fun to watch. I love every day there's something. It's so fun. Yeah.
Oh, by the way, I have to thank you guys for the inspiration that you guys provided for the Walking on Water series this week, and also for sending me all those papers. That was very helpful as well.
I think that's our next question, if you have time for one more.
All right, time for another one.
Can you tell us a little bit about your research process, how long it takes, because you're putting these up so often, and then, maybe briefly, like, what went into the calculation for this week's, big reveal sort of on Friday. So, yeah.
All right, so the research process is, it varies a little bit depending on what's going on. Like sometimes I have an idea of what it is that I want to be writing about, in which case it's a little bit easier to go about searching for the material. So some days it's that I have an idea and I go out and I basically Google is my best friend and I find some kind of information and some visual, and then I can put together an entry. And other days I don't have a good idea and I'm just out there searching wildly on YouTube and Google image search and whatever else I can come up with in order to find something that I think might be a good idea. Sometimes I'll scan whatever the newest papers out of different fluid dynamics journals are in order to look for stuff. The research process depends on the topic. In many cases, I can write something just on my own. In other cases, I have to read one or more papers and sort of try to digest them and figure out how do I go about explaining this. It kind of varies from topic to topic. How long it takes also varies. I mean, I think I've written some FYFD posts, like researched and written some of them in under an hour, and other ones will take many hours in order to get through. Or in some cases, I'll come up with an idea and I actually end up spending days or weeks or months between coming up with the idea and actually getting what I need in order to make the whole thing come together. I'm definitely discovering with videos that that's very much the case too. Like some videos I've been working on for more than a year now, actually, between coming up with the idea and developing the film and figuring out the research and everything else. So it's turning into quite the ongoing process. As for this week, so because I knew that I wanted to do a theme all around walking on water, the inspiration was partially that I knew I was going to have this webcast with you guys, but also in just going out and looking for stuff for FYFD, I'd come up with a couple of papers, the one about the grebes and the one about the water strider robot. And I realized, hey, these both kind of have to do with the same sort of thing as what we're going to be talking about. Why don't I just do an entire week's worth of posts? And from there, like some of the other topics came out kind of naturally. I'm not even sure exactly where I got the idea for Friday with doing the Flash running on water, but I do enjoy watching the Flash TV show. I will confess to that. I have a little bit of a superhero addiction these days, and so it was really kind of fun to dig into the physics of that.
Yeah, and the online calculator. So did you just, do you grab the article, is it Glasheen, I think, article, and then you just, like, how does that work? What's your process? You just pull out those equations and then just get some questions that you have generally and try to answer those. And, maybe at what point do you say like, okay, I'm just gonna make this assumption and then you're on, you know?
So actually, that is actually the first time that I've tried to do something like that, where I actually build a calculator that was going to go with an FYFD entry. So this yesterday's post was kind of significantly different for me in that regard. So instead of just writing a quick paragraph, it's actually a very long post, and it comes with the calculator. And to do that, what I did was I actually looked at both Glasheen and Minetti and a couple of other papers, and I basically reconstructed the model myself mathematically from what they were saying, like here, you know, for this phase and this phase, and these are the things that you have to fulfill. And I made some similar assumptions to what they were making, and I kind of tweaked things to make sure that when I was doing all of that mathematically, I could put in inputs that were consistent with what other researchers had said and get answers that were consistent out. For the most part, the equations that are in that calculator are the same ones that are printed in those papers. I will say there is one exception. There's actually a typo in the equations in Minetti, so I corrected that typo, and that helped my numbers come out a little bit better. The one place where I did kind of extend the model on my own was in trying to translate from the impact speed that your foot hits the water at and figure out how fast forward you would be going as a result. That was a little bit more complicated because all of the model is just set up to figure out how fast you have to hit the water in order to generate the vertical force lift that you need, essentially. And they don't care about how fast that actually means that you're going forward. So in order to do that part, I actually looked at the data that was in, I think, Glasheen's paper and the Grebe paper, the authors of which are, and when I say it was maybe Clifton et al.
Okay.
But they had experimental data for this is about how fast these animals run versus this is what their peak impact velocity was. And I used that to create a linear model to predict how fast a person would be moving forward based on kind of the characteristics of their results from the existing model. So that was actually kind of an interesting thing for me because it was utilizing some of the skills I had from industry to try and build some physical models and put it in there. And then there was just trying to teach myself JavaScript very quickly in order to write the interior of the calculator because I'm used to doing all that kind of stuff in MATLAB instead.
Well, that's cool. That's a long process, but really interesting. I think for people that are just daily readers, it's really interesting, I'm sure, to figure out how that works. I mean, it's not that much different what we do, but you do it at a rapid pace. I mean, we go fast too, but I guess we're trying to like get new information, so it does seem like it takes us a lot longer, like a year-long process for a paper to develop. But I don't know, maybe we're going too slow. I don't know.
You guys are also collecting the data, and I'm sort of taking the data that other people already had. So the actual process of putting together getting all of the research read and processed, and that calculator written was probably about a day and a half.
Okay.
I spent most of Saturday last week kind of getting obsessive over it to the extent that I spent my Saturday evening doing that. Not too ashamed to admit.
Well, do you want us to show you one more experiment? We have another one right here.
All right, let's do one more before we wrap up.
All right, I'll bring this over. Let's see. Let's do it on there. Yeah, let's bring this down. Okay, sorry, I got to move on that better. Oh, yeah, you want to do that? Great, let's do it.
While they're setting up for that, I will note, if anyone has any final questions that you want to ask, you should probably go ahead and submit them because we're going to sign off at 2 p.m.
Okay, so before we start, I just wanted to show you two quick things. Can you see? Okay. Can you see this, though? I can't.
It's really dark.
Oh, here, I'll do this. Sorry. How about, is that better?
That's much better.
I just wanted to kind of show off just two things really quick. So we got an experiment we're going to do, and it's going to be backlit, so it's going to just be dark, light and dark. That's okay. But before we do that, I just want to show you, this is the largest ball we tested for the Waboba project.
It's like softball sized?
It's a little bigger than a softball, but it's about 4 inches in diameter. You can see my hand there holding it. Put it next to my face. It's the size of a very large tumor. Anyway,
Thanks for that image.
I would say grapefruit size. So anyway, yeah, and you can see here, if you look really carefully, you can see the stitches.
Yep.
Randy actually makes these by hand. This is the largest size. In the paper, we use a numerical model to go all the way up to a meter diameter ball, just so we have these extremes. And then the smallest one we make, I don't have here, but it's a little smaller than this one. If you open them up, you know, and tear into them inside, you'll find they look a lot like this. It's just silicone, and it's basically molded together. This one has been cut in half so that you can see it there, and you can see there are voids in it even. Okay. Then what we did was Randy made these molds. They're kind of heavy. Can you see this mold here? Let me turn this down. So you can see there's a mold there, yeah. And then here's what the inside of it looks like. Can you get that over there? You see that? So then there's this cavity. We stick them together, and then we pour the fluid into that sort of gap there. And then this is what you get when you're done. You pull one of these out and have this nice sphere that then you can put these what are these? Neoprene coating? No, is that right? Neoprene? Lycra. We do like a lycra.
Oh, it's just like a cyclist.
Just like a cyclist, we put them in their own spandex. So that's it. So I thought that was kind of, I don't know, it was interesting. We had it out, so I'll show it. And
yeah, and that's essentially what the inside of these guys look like. Only by making them yourself, you can control the coefficient of restitution in there.
That's right, and we use some stuff called dragon skin, and we add a certain amount of thinner. And the more thinner we add, the more elastic they become. In fact, you can get it so elastic that you put it on your hand and it kind of like oozes over the edges. It won't fluidly like leave, but it's just like hanging there, you know. And of course, those balls are really hard to shoot out of a cannon. So in those cases, we also use the numerical model. So the very low end of the elasticity is numerical. And so I thought this was a cool problem. We had to collaborate with some people at the Naval Undersea Warfare Center, Jesse Belden and Mike Jandron, as well as Alan Bauer at Brown, because we couldn't do that part of it, you know. And then, of course, their models are so awesome. It really coupled this whole problem together. So between the numerics and the experiment, we got this really great problem, which I thought was a lot of fun. Okay, Randy's going to give us an experiment, a test here. I've got to wipe my hands off. Give me 1 second.
I like in the background there, for those who can see it, there's this picture of cavitation shattering a glass bottle back there.
Yeah, right. Let's see.
Just one of my favorite of their gallery fluid motion videos, and it's one you can find on FYFD. Yes.
We like to do that one live. I love doing that one in person. It's so fun. But we didn't bring that one today. I'm sorry. I didn't know it was I didn't know you loved it. We would have done it, but
I love just about everything you guys do, to be fair.
Oh, thanks. That's so nice. Okay, here, let me go like this and get Randy. Here's going to do an experiment for us.
All right.
Okay.
So, okay, finally the demonstration is the effectiveness of aiming for a urinal pad. So you have to tip down, I think, a little bit, Chad.
Okay.
There we go. There it is out there on the board.
How does that look?
That looks pretty good. I can see what's going on here. So we've got a bowl, it looks like, and then a wet surface up top of it.
Yeah, the bowl's upside down just to hold the object.
So a wetted surface, this is kind of like, urinals are usually wetted because they flush and are used so often. This is if a male is aiming for a traditional wetted urinal, something like this is going to happen.
And so you can see our plexiglass plate here we have in front of us is now wetted. Can you see that okay?
Yep, we can see that.
Okay, great. And so what Randy did, I'll pull this thing from around here. What he did was he used the back side of this thing so it's flat. Can you see that it's flat there?
Yep.
Okay, now, are you going to use this one?
Yep.
Now he's going to use the other side, which can you see has like these pillars that are spaced a certain distance apart and they have a certain height to them?
Yep.
Is it resolution good enough to tell? I don't know, but anyway.
I can tell.
Okay, great.
I can see the light through there.
Yeah, okay,
See
good.
if we see any difference.
Oh!
That looks like your khakis are going to stay dry.
Yeah, exactly. So we thought that was pretty cool.
How about that?
What do you think? that pretty good?
You know, I don't have this problem.
Oh, okay. Well, that's not entirely true.
I have different problems.
Oh, okay. Well, I don't know. I guess, yeah, but it's still a real problem.
No, it is very cool, and it's a very good way of demonstrating. That would be the urine black hole. If you saw headlines about that, those of you who are watching, you just saw the urine black hole.
Yeah, it's cool. It's a lot of fun. So,
All right.
Yeah, that's great.
All right, guys, thank you so much for joining me. This was so much fun.
Thank you, Nicole. Thanks so much for having us, and we're really honored to be
Happy to be here.
one of your guests. Thanks so much.
Awesome. Everybody who tuned in, thank you for tuning in. I hope you enjoyed this, and join us next month when we do this again. I'll figure out a new guest soon and let you guys know. And in the meantime, happy fluid dynamics.
Great. If you have any questions, let us know. Have a nice afternoon. Thanks
Bye,
so
guys.
much, everyone. Bye-bye.